I get to record for 29 minutes, I can afford 2.5 minutes per frame. Right, somebody mentioned tides. Some flurf said, how is it that gravity can hold the ocean down yet the gravity of the smaller moon can pull it up into a hump? Well, if you've seen diagrams like these you may have thought they looked a bit silly. Of course, most people would kind of understand that having strong gravity of the Earth pulling inwards and the weak gravity of the moon pulling that way would create this slight hump. This would be the one that was harder to explain. There are a few problems with that diagram and that explanation. One being scale. To scale, there's the Earth, here's the moon, at perigee as close as it ever gets, or apogee as far away as it ever gets, relative sizes and distances drawn to scale. Scale of the actual Earth-Moon system, not quite as relevant to that not making sense as the scale of the tides relative to the Earth. This across the bottom is a small part of a circle. It may look straight because it's such a tiny piece of a circle, that is a curved line. The upper edge of that black strip is a part of a circle. Over here I've got the 100-metre high famous White Cliffs of Dover with the slightly high ground behind them, which have radar on top for some reason. They put them as high up as they could without moving them far back from the coast. For whatever reason they do that kind of thing. And Kent. This will be the English Channel, France is off this way to the right. This little tiny blur here is a scaled down version of an image of the motor vessel Spirit of Britain. I have another scaled down version, but scaled down to a considerably larger size here. Scale down to just the right size for the thickness of this green line to be the height of the mid-ocean tidal range. Yeah, the thickness of that green line that you might not even be able to see. It's there. Now if I zoom right in, that green line is to scale with that image of the liner for the mid-ocean tidal range. You get higher tidal ranges at coasts because putting a rock in a stream affects the flow of the water. But in terms of the height of the bump on the moon side or the side opposite the moon, scale that thickness of that green line down so that it fits this tiny blurred image down here and think how small that is compared to the circle of which this is a part. And there you've got, just for extra scale detail, there's an airliner up here cruising at 10 kilometres. That gives you an idea of how thin that little blue layer and the bulge in it, actually just of how thin the bulge in that little blue layer should be on a scale drawing. Obviously it wouldn't show up, which is why they don't draw them to scale. The other reason that the not to scale drawing showing two bumps won't make sense is that you probably think of the moon going around the Earth like this. Here I've got apogee and perigee and the Earth to scale with diameter, at least roughly. It's kind of small scale, so near enough. With the moon going around out here on its course around the Earth, which is rotating, which is how you probably think of it, and that's probably fine. Earth rotating at a dizzying speed of 0.000 0.0000729 radians per second. For a lot of purposes, if something is 0.000 something, you just call it 0, but 0.0000729. Meanwhile, the moon is going round at 0.0000266 radians per second, which is considerably slower. This diagram works just fine if you're in an Earth-centered frame of reference and you're not worried about tidal physics. But it's wrong. Imagine, if you will, if you're in the USA, imagine a 40-pound kid sitting on a 10-pound toy tractor and a 30-pound kid sitting on a 6-pound toy tractor connected by an elastic rope. If you're not in the USA, imagine a 20-kilogram kid sitting on a 5-kilogram toy tractor and a 15-kilogram kid sitting on a 3-kilogram toy tractor connected by an elastic rope. Pull those two vehicles as far apart as you can, or maybe not as far apart as you can, depends on the rope, but stretch the rope between them by pulling them apart on a nice level surface, polished concrete floor or whatever. Toy tractors would really smooth the bearings and then let go. Is just one going to move, or are both going to move? Obviously both. The weight ratio here is a bit different, or the mass ratio I should say. This is more like a 40-pound kid in a 9-pound toy tractor and a 186-pound bloke in a 3,800-pound 4x4 pickup truck in neutral. Stretch the rope between them, let go of both. Obviously the kid on the toy tractor is going to accelerate a lot more than the guy in the truck, but they are both going to accelerate. The same force, tension in the rope, or gravity in this case, is acting on both. And because the acceleration of an object, the inward acceleration of an object moving in a circle, is proportional to the radius of the circle, and the force of a mass, the acceleration of a mass on which a force is acting, is inversely proportional to the mass, the ratio of the radii of the circles from some point here out to the moon and from the same point out in the opposite direction to the Earth must be the same as the ratios of the masses of the mass of the Earth to the mass of the moon. This ratio here, which gives us a position of this point called the barycenter, which is inside the Earth but nearer to the surface than to the centre. And the same thing happens with the Earth-Moon system over on the right. 4 pixels apart is to scale with the width of the empty space between them in that image, but they are drawn 1 pixel size where there should be a 7th of a pixel and a 25th of a pixel to be to scale. Over on the left is a yellow blob for the Sun, and the distance from the centre of the Sun to the Sun-Earth barycenter is 4.5 million pixels. Doesn't show up. Even if you zoom in, it doesn't show up. If you want it to show up, you need something more massive than the Earth and further from the Sun. Jupiter's a pretty good example. It's over here, it's a pale creamy colour, 1/4 of a pixel wide, but it's drawn as a whole pixel so that it shows. Is to scale with that distance. On this scale, the Earth is about 1/40th of a pixel wide, tiny little speck there. And the Sun is less than 3 pixels wide, with the Sun-Jupiter barycenter 1.5 pixels from its centre, so it still doesn't show, but if you zoom in on that, it does. Yellow is the photosphere, the part you see. Outside it is a very thin pink layer, the chromosphere, which is not visible except with really fancy equipment and or under peculiar conditions. And the Sun-Jupiter barycenter is just out here. You can actually look up, I'm not quite sure what search terms are best, but you can look online and find illustrations of the way the Sun, the inner planets go around pretty much the centre of the Sun. The difference is kind of negligible, but the way the whole inner system and the outer planets dance around this barycenter, which is sometimes inside and sometimes outside the Sun, because obviously Saturn is also a long way out and massive. Going back to the Earth is going around that barycenter, which is somewhere around about here where the mouse cursor is. Which means this part of the Earth's surface is going that way, this part is going that way, the centre is going that way, this part is going a heck of a lot faster than this part. A heck of a lot faster on a very slow scale, because this is once per lunar month. But it is going faster. And an object is going in a circle is accelerating inwards, so this point is accelerating this way, this point is accelerating this way, this point is accelerating this way. Now that is not straight down, that is an angle. I'll come up later. Let's have some equations. Forces, mass times acceleration. Yes, we're doing Newtonian physics. We're not dealing with black holes, we're not dealing with 90% the speed of light, we're dealing with very slow moving objects, piffling, 19 miles a second kind of velocities. It's not the number I remember. Forces, mass times acceleration. Good enough. G, force of gravity, equals big G, universal gravitational constant, bizarre units. It's around about 6 times 10 to the minus 11 cubic meters per kilogram square second. Multiply that by a mass in kilograms and by another mass in kilograms, and kilograms times kilograms per kilogram is kilograms, and divide by a distance in meters squared. Well, you've got cubic meters, dividing it by square meters, you're left with meters, and you also have the per second squared. This gives you kilogram meters per second squared, which is newtons. Flip this formula around, because it's equals and multiplication, they can be flipped. And when we're talking about gravity, the force is the force, so the force is the force. Sounds very Obi-Wan Kenobi. Acceleration times mass equals force of gravity equals g(m1m2) over r squared. You can knock out the bit between the equal signs. Acceleration times mass is big G times one mass times the other mass divided by r squared, and of course you have that mass is one of these two, so you get A equals gm over r squared. Gm with a capital M is a number given for planets, moons, stars, whatever. Figuring out the exact gravitational constant, kind of difficult. They have fantastic experiments with fountains of individual rubidium atoms in a vacuum and all kinds of stuff. Weighing planets, well, finding the mass of a planet. Also interesting and difficult, finding GM for a planet, for an orbital body is easier to get accurate and get consistent results everybody agrees with. So you get GM for these things. This is a couple of pages from NASA, all kinds of stuff on them. nssd.gsfc.nasa.gov/planetary/factsheet/moonfact.html. Or you could just Google it. They have Sun fact, Mercury fact, Venus fact, Earth fact, Moon fact, Mars fact. I think they've got Phobos fact and Deimos fact, Jupiter fact, Saturn fact, Neptune fact, Uranus fact, Pluto fact, Ceres fact, probably Titan fact, Io fact and Ganymede fact as well in there. All kinds of stuff about mass, volume, equatorial radius, polar radius, the works. GM is one of the things given. This is from the Moon one. It actually gives you the Moon and Earth and the ratio between them. And this is in 10 to the 6 cubic kilometres per square second. So a cubic kilometre is obviously 10 to the 9 cubic metres because it's 10 to the 3 cubic metres on each of 3 sides. 3 times 3 is 9. So that is 10 to the 15 cubic metres per second squared, and 0.0049 is 4 times 10 to the 15 is 4.9 times 10 to the 12. Just move the decimal point 3 places across to the right, subtract 3 from the power of 10, same thing. And Earth, 0.3986 times 10 to the 15, which is 3.986 times 10 to the 14. Also of interest, the revolution period. I actually got a better number for this from a different source. That's how long it takes the Moon to go around the Earth relative to the background starscape, not relative to the Sun. Relative to the Sun is this one down here, 29.53, because the Moon has to go more than once around the Earth to line up with the Sun, because the whole Earth-Moon system is going round the Sun. Over here on the right, we have Earth orbital parameters. Sidereal rotation period is how long it takes the Earth to rotate once, again relative to the background starscape, not relative to the Sun. Relative to the Sun is slightly longer than this, because again, it's going round. It's orbiting around the Sun, it has to rotate more than once to line up the same meridian with the Sun again. It is 23.9345 hours, or 86164.0905 seconds. All sorts of other stuff. Particles per cubic, 2 times 10 to the 5, also known as 200,000. Particles per cubic centimetre on the Moon, it even tells you the ratios. And 1.217 kilograms per cubic metre of atmosphere on the Earth's surface, and all kinds of stuff about them. We'll use the GM numbers, the GM and the revolution period and sidereal rotation period, to put in, oh my god, there are all kinds of equations in all kinds of colours on here. This is an equatorial cross-section through the Earth, perfect circle, across the middle of an oblate spheroid. In purple, gravity towards the centre of the Earth, given, and it's the same all the way around the equator. GM for the Earth divided by equatorial sea level raised to the Earth squared is 9.798 blah blah. In green you have the centrifugal effect, which technically is how much of that acceleration is used up just staying on the Earth because the Earth's surface is accelerating inwards. If you're in one of those barrel rides at the fairground, you feel yourself pushed against the wall. Actually the wall is pushing on you, pushing you inwards to make you go around in a circle and stop you flying off in a straight line. But it amounts to the same thing. Effectively, you've got 0.0339 meters per second outwards relative to this rotating frame of reference at any point, which gives you this net acceleration. In orange, we've got the centrifugal effect, which will be almost the same up here and down here, one slight difference. Rather different here and here for the Earth orbiting around the Earth-Moon barycenter. Down here, it's quite a small orbit, because it's close to the barycenter. That's your rate of rotation squared times a radius, which is the radius of the Earth minus that distance, so just this bit here, which gives you 0.00001065. On the opposite side, same equation, but it's this radius of the Earth plus that distance for that radius, so 0.0000800309, considerably bigger. Also outwards, straight up from point of view of someone standing there. Here and here you get this equation where you've got the same orbital angular velocity, but the distance is by Pythagoras, which is the square root of the sum of the squares of that distance and that distance. It's the length of this hypotenuse. And that gives you this 0.0000572231, which has to be multiplied by the sine of that angle to give you how fast it's accelerating you this way. relative to the surface, and by the cosine of that angle give you how fast it's accelerating you upwards, outwards. Out from the circle is up from the point of view of someone standing there. If this is a view from the North Pole, this will be accelerating you east, which is this way. Down here, it'll be accelerating you west. Either way, away from the moon. And in red, we've got the moon's gravity, 4.9 times 10 to the 12 divided by this phenomenal distance, 400 million metres. On this side of the Earth, 400 million metres plus the radius of the Earth. On this side, 400 million metres minus the radius of the Earth. And in the centre, also 400 million metres. Technically, it's a little more than that out here, Pythagoras and all that, but it's not much different. And that gives us these totals, which is Earth's gravity plus the moon's gravity minus the centrifugal effect and minus the other centrifugal effect, good even talking too fast. Also minus how fast the Earth itself is going that way due to the moon's gravity. Give me this number. Over here, likewise, you are being pulled towards the moon faster than the Earth itself is, because you're closer to it. So it's the difference between them, plus the centrifugal effect, plus the two centrifugal effects. That one, up, out from the circle this way, and Earth's gravity inwards, giving you this total. And up here, it's Earth's gravity downwards, centrifugal effect of the Earth's rotation upwards, gravity to the moon west, and centrifugal effect from the Earth orbiting the barycenter up and east. So the total up here actually includes a westward component, but it's a westward acceleration at 0.000035 metres per second. Really bloody slow. And a downward acceleration at 9.7643 metres per second. So your weight, if you were at a point on the equator 90 degrees from directly under the moon, would be that times your mass. If you're opposite the moon, 9.764277,647, which is bigger. Is it? No, it isn't, because that's a 2 and that's a 3. It is smaller, 9.76427776 versus 9.76431124. This is smaller. Over here on the side nearest the moon, 9.764287 if you want to round it, or 2866 if you want to round to that many significant figures. Again, smaller than this. Slightly higher on the side nearest the moon than on the side furthest. Kind of counterintuitive. But what you have is greater weight for the same mass, 90 degrees from the moon, than nearest or furthest from it. That's why you get two bulges, one nearest and one furthest away. If we flip this from the equator cross-section to the polar cross-section, you can tell it's a polar cross-section because it's not perfectly circular, it's elliptical, as you can all see. Everyone has ever complained that, NASA tells you the Earth is oblate, but every photograph they show you is perfectly round. Well, there you go, there's a photograph of an oblate ellipse. Well, a cross-section through an oblate spheroid, an ellipse. As elliptical as the Earth. Here you've got north and south poles, and there you go, centrifugal effect away from the moon, moon's gravity towards the moon. The Earth's rotation creates a centrifugal effect at the equator here and here, but not at the poles here and here. So you don't have any green text in the polar calculations. And the totals here, you have the same around the equator, but at the pole 9.864311, so again more than both of these. Again, you weigh more at the pole than at the equator. So what you have is the lowest weight nearest the moon and further opposite the moon, and the highest weight in a band that's 90 degrees away from the moon all the way around, equator and both poles. And one more thing to take into account, the influence of the sun. On the left, the circular cross-section through the equator, on the right, the elliptical cross-section through the poles. Visibly very different. And we have acceleration due to the sun's gravity. 1.32712 times 10 to the 20, because the sun is massive. It has mass. divided by 150 billion if you're American, or 150 milliard if you're British, squared, plus the Earth's radius squared. Divided by the square of the distance, and the distance is the square root of the sum of the squares of those two, so just divided by the sum of the square of those two. With the sun off to the right in both images, hence these arrows. 0.0024 degrees. And yeah, the sun's quite a long way away, so being one Earth radius out to the side doesn't make a whole lot of difference to the direction. Out here on the equator, 9 degrees away from the sun, 0.00589831111. On the North Pole or the South Pole, 0.00589831111. In the centre of the Earth, 0.00589831111. On the equator furthest from the sun, 0.00589780810 even. And on the equator nearest the sun, 0.005898813. Sometimes you have to use an awful lot of decimal points to actually see the difference. If you subtract the centre of the Earth gravitational pull, which is how much the whole Earth is accelerating towards the sun, from each of these numbers you get the differences. And the differences give you, on the equator 9 degrees the way around, there are, I believe, 10 zeros there between the decimal point and the 1. This is why you use scientific notation. It's 1.0664 times 10 to the minus 11. It's easier than just counting the zeros all the time. Meters per second away from the sun relative to the Earth, because you're just that little bit further away. And at the poles, 1.0593 times 10 to the minus 11, because you're not quite as much further away, but honestly that is so small. 10 to the minus 11 meters, that's like 10 picometers, I think. We're talking intramolecular bond lengths here. But on the equator, the difference is a whole 5 times 10 to the minus 7 each way, which is 501 nanometres, so a whole virus width per second. On the side furthest from the sun, you've got less solar gravity pulling on you than there is on the Earth, so it's pulling the Earth away from you, and effectively you get less weight. On the side nearest the sun, you have more solar gravity acting on you than there is acting on the Earth, so it's pulling you away from the Earth and you get less weight relative to the Earth. Not by much, but it is there, and that creates the bulge towards and away from the sun. And of course the bulges towards and away from the moon and the bulges towards and away from the sun add up to give you neap tides if they're at right angles and kinda cancelling each other out a bit, or spring tides if they're both lined up, both pulling in the same direction. So you should get the highest tides at full moon and new moon, and the lowest tides at half moon. And that is how. Hey, 23.5 minutes. That was a lot faster than it might have been.